Alright, on section 2.6 we're finally going to get to some calculus called the derivative. The first thing we're going to look at is the average rate of change given a graph. Now that sounds very fancy, but all that is the slope of a tangent line. And I want you to remember that throughout this lesson. Right? And then the book calls this a four-step process to find the slope of the tangent line. We can shorten that. And then we're going to use the definition of the derivative in some particular problems. But first of all, let's just look at what a tangent line is. A tangent line is a line that's just going to touch a curve in one particular point. Sometimes that's hard to see. All right, so you've got this graph here that's curvy, all right? And apparently it is the volume of wood produced in a forest. Right, so you can see that if you drew different tangent lines, those tangent lines have different slopes. Like this one has a smaller slope than that one because it's less tilty. All right, so we're going to find T1, which is the slope of this first tangent line. Now if you recall, the slope is rise over run. And so we're going to be asked to find the average changing at the beginning of year 10. So they've drawn us a tangent line at year 10. Here's this line. And if you look real carefully, they've made this little bitty triangle. Well, that's the rise and run. So the run is from 10, well, a little bit past 20. They tell us it's 12. So the run is 12. And the rise is 4. So the slope of this first tangent line is just 1 over 3. All right? Now we should expect the slope of the second tangent line to be bigger than 1/3 because it is a lot steeper. And so that's where they're asking us to look at the average change or the slope at year 30. And again, they've gone up here. They put a dot at year 30, they've drawn a tangent line, and they've done this triangle thing, and they've done rise over run. Now notice that that 10 is going all the way up to the tangent line. It doesn't stop at the curve, right? So we want rise over run. Well, the run was 8, the rise was 10, and so if we reduce that, that's 5 over 4, and that is definitely larger than 1/3, which is what we expected. So the first couple of problems, you're just looking at a graph. This graph shows a secant line, the line joining 2 points. But look at what happens to the slope of that secant line as those 2 points get closer and closer to each other. Of course, it changes. But what happens when those 2 points get on top of each other? The slope becomes undefined. Let's see why that is true. So recall, the slope of a line, as we talked about earlier, is just the rise over the run. But mathematically, you may remember from algebra class that it is really y2 minus y1 divided by x2 minus x1, or you may have seen it as delta y over delta x, meaning the change in y over the change in x. So how am I calling the slope of a secant line f of x plus h minus f of x divided by h? Oh goodness. So this graph, if I'm at the point x, then the y value is the function evaluated at x. So this point is really x, comma, f of x, instead of x and y. This point has an x coordinate of x plus h because I moved that far. And so this y value is the function evaluated at x plus h. So as we go back and look at that part of the formula, the difference in the y values is really this minus this. And that's how we get that numerator divided by the difference in the x values, well, that's the distance between the x's. In fact, if I were to take x plus h and subtract x, I would only be left with h. So the slope of a secant line is given by this formula. Another way to say is that it's the average rate of change. Now, of course, as we saw in the previous little demonstration, as this point gets closer, our slope is going to change and our h is going to get smaller as we move closer and closer. So my question is what happens when h is equal to 0? Well, hopefully you remember that you can never divide by 0. So what's up with that? Well, this is where the calculus comes in and the idea of a limit. So we've talked about the limits in the earlier part of the chapter, saying what is the y value getting closer to as x is approaching some value. Now we're going to look at what happens when the distance between our 2 points gets closer to 0. And that is called the derivative. Instead of a secant line, we have a tangent line. Because that distance is really 0, instead of having 2 points, we have 1 point, and we want to find the slope of the tangent line. And that is indeed the definition of the derivative. It is the limit as h approaches 0 of f of x plus h minus f of x divided by h, and then of course we need to take that limit. So let's go back to basics. What if we were to graph f of x is equal to 5? Well, hopefully you remember that that is a horizontal line. So what is the slope of a horizontal line? You should remember that the slope of any horizontal line is 0. In other words, this is a constant, because a number without a variable is just a constant. That slope would be 0. But how could we apply the definition of the derivative? Well, it's a little bit odd because we don't have any x's. But the function evaluated at f of x plus h, so let's pick any point x, and over here some point x plus h, what are our y values? They're both 5. So we would have 5 minus 5 divided by h. Well, that's 0 divided by h, which is 0. Now notice I haven't taken the limit yet. The limit as h approaches 0 of 0, well, there's no h either. It's still 0. Now that's kind of odd, but the important thing I want you to remember is that the slope of a constant, or in other words, the derivative of a constant, is 0. Remember, that's just the slope of a tangent line. And in this case, the line is the tangent line. So that kind of lets go to another line. If you remember, this is in the form of y equals mx plus b. So we have a y-intercept of 5 and a slope of -3. So if I wanted the slope of the tangent line, well, a tangent line is just going to be the line. We should know from algebra that our slope is -3. In fact, that would be the derivative of this function. It's going to be the slope of that line. But let's use that definition here. Well, so let's see. I need to find f of x plus h. So f of x plus h. That's -3 times x plus h plus 5. And then I need to subtract f of x. All right, so I'm going to kind of cheat here and say, so now I have this, and I'm going to subtract my original function, and divide by h. Let's see what happens. So this would be negative 3x minus 3h plus 5. I need to distribute that minus sign. I need to collect like terms. And look at what I'm left with. I'm left with a negative 3h divided by h. I can divide by h and just be left with negative 3. So again, if I say the limit as h approaches 0 of negative 3, it's just negative 3 because there is not an h involved. So you're going, well, that's pretty easy. What happens if we don't have lines? So the book refers to the four-step process to find that derivative. And I don't really care if you use all 4 steps. What I do care about is you use the definition of the derivative, and this is that definition. So you would need to show all of the work involved, whether it's 4 steps, 3 steps, or 2 steps. So we're going to look at this function, not a line. So how am I going to find the derivative when I'm asking for the slope of a tangent line? Well, there's infinite amount of tangent lines. I could say, let's put a tangent line here. That would have a positive slope. I could have a tangent line here. That'd be a slope of 0. I could have a tangent line here. That would be a negative slope. So what we're going to find is the derivative in general. So let's go through those 4 steps. So step 1 is to find f of x plus h. So wherever there's an x, we're going to put in an x plus h. We practiced this earlier in the chapter, so hopefully you're pretty good at it. Okay. Again, the second step is to subtract f of x. So I'm going to have, again, I'm going to kind of cheat a little bit. I'm going to have that, and I need to subtract my original function. Okay, so again, if I distribute my minus sign and collect like terms, I'm left with just those 2 things. So then it says, hey, well, let's divide. Okay, so trying to be a little bit neater. 4xh plus 2h squared divided by h. Since all the terms have an h, or in other words, I can factor out an h, I can divide and be left with 4x plus 2h. Now the last step says to find that derivative. Notice this notation, this little prime mark. That is one of many symbols for the derivative. And it says the last thing I need to do is to take the limit as h approaches 0 of 4x plus 2h. So we've talked about limits a lot. As h gets closer to 0, this is going to approach 0. And so my answer is 4x. This x is a variable. And that makes sense because depending on where I draw that tangent line, my slope is going to vary. Ergo, that's why the derivative does have that x involved. So let's just practice that algebra of finding the definition of the derivative. So step 1, I'm just going to find f of x plus h. Again, everywhere there's an x, I'm filling in an x plus h. You want to be really careful that you want to square this out first, then distribute that minus sign. Okay, the second step is to subtract your original function. So I'm going to take that result and I'm going to subtract my original function. So you just have to really remember to distribute that minus sign. So I want to distribute here to everything. Then collect like terms. Simplify, so we have this minus this plus this. And then the last step, well, not the last step, sorry, we need to take this and divide by h. So notice every term has an h, so that means I can factor that out and reduce that h. So that's really step 3, if you will, right there. And then step 4 is to take the limit as h approaches 0 of what I've got left. And of course, as h approaches 0, that leaves me with just negative 2x plus 3. And that would be the derivative of this function. So really I could say the derivative of f of x is negative 2x plus 3.